Thank you. It's a privilege to be here. Appreciate the invitation. I'm lucky to have had Nina give a fabulous talk yesterday that introduced many of the things I want to talk about today. I realize maybe not everybody was here for yesterday's talk, but I think most of you were. So I won't spend too much time on that, but I actually want to back up a little bit and start as I think is appropriate for being in this place at this time, and also related to the first talk I gave in this room, which was about the Sato-Tate conjecture. And with Peter and Nick in the audience, I thought it's appropriate to start there, but it also has relevance to what I want to tell you about today. So, I mean, I think the reason I mentioned I think this is useful framing is if you're going to think about distribution of Frobenius traces to elliptic curve, you know, we're looking at some very fine, detailed behavior that's quite subtle, but maybe we should start by thinking about what should we expect sort of in the large. What is, you know, what are the general things we know about distributions of Frobenius traces? And the Sato-Tate conjecture, formulated in the early 60s, maybe either contemporaneously with or maybe even slightly before the Birch and Swinnerton-Dyer conjecture, is a conjecture about how if you take a fixed elliptic curve and you look at its count points on its reduction modulo p, you can compute the trace Frobenius as p plus 1 minus the number of points on your elliptic curve mod p. We know those traces are real number or integers between -2 root p and 2 root p. And so if you divide by root p, you get a real number between -2 and 2, and you could ask, how does that real number vary as p varies? And the Sato-Tate conjecture makes a very precise prediction for how it varies. And the answer is it varies the same way the trace of a random matrix in SU2 varies if you sample with Haar measure. And one can generalize this notion beyond not just for elliptic curves over Q, but for abelian varieties over number fields, or more generally for an arithmetic L function. In a sense, I'll make a little more precise a bit later. The original Sato-Tate conjecture, I should say, is no longer a conjecture, it's a theorem approved by Richard Taylor and many co-authors, and they have since developed more powerful versions of the same methods, which sort of build on modularity but add quite a bit more to prove the Sato-Tate conjecture for elliptic curves over totally real and complex CM fields. And the last result is quite recent. I think it's famously known as the 10-author paper. So I'll just start with an example for those of you who haven't seen it before. Well, let's just take a typical elliptic curve over Q. Put typical in quotes, because maybe this curve doesn't look so typical to you. This is an elliptic curve of rank 28. And you might guess that maybe there's something atypical about it because its Frobenius trace distribution is very skewed to the right. Now, I'm actually plotting the coefficient of the L polynomial, so positive to the right actually means a negative trace, which is what you'd expect. You should expect an excess of points at small primes if you've got rank 28, because you've got 28 rational points. You can reduce the mod p, they're all going to be rational points mod p. But let's see what happens if I can manage to click this. Okay. So in each frame of this animation, what's happening is I'm sampling more and more Frobenius traces. The sample size is doubling roughly in each frame. So the bound on P is increasing with powers of 2. And then I'm computing APs for all the P's up to that bound. And even though this elliptic curve has rank 28, and you might think it should have an excess of points, the Sato-Tate law forces it into a nice smooth semicircle in the limit. And we know that this happens for any elliptic curve over Q that does not have extra endomorphisms, does not have complex multiplication. Okay, so in general, there are actually 3 different trace distributions that can occur for elliptic curves over Q. There's the generic one. If you have, elliptic curves over number fields over Q, there's 2. You either have CM or you don't. But over Q, the CM is really potential in the sense that your endomorphisms are not defined over Q. So the Sato-Tate group for a CM elliptic curve where the CM is actually defined over the ground field is given by the Haar measure. The trace distribution is given by the Haar measure on U1 embedded inside SU2. And if your CM is not defined over the ground field, as would be the case over Q, the Sato-Tate group is actually the normalizer of that the circle group inside SU2. And that's why you get a spike in the middle, which is where you have super singular reduction. That spike has density 1/2. So half the mass is on that spike and the other half is in that semicircle. So this whole notion of predicting Frobenius taste distributions with random matrix models has been vastly generalized, most notably by Katz and Sarnak, who are here in this room.
Wrong initial.
I'm sorry?
Wrong initial
of E, period.
Ah, there's a period. Yeah.
No, it's the E that's wrong.
Okay. Well, the E is referring to an elliptic curve, and I'm referring to the Sato-Tate group of E. And then I'm saying that Katz and Sarnak and Sayre extended this. Yeah, so I should probably, normally you try to avoid starting a sentence with a math symbol, but I guess I should also avoid ending a sentence with a math symbol. It could look like an initial. But they famously extended this model to higher genus. In general, one expects for a generic abelian variety of dimension G, the Sato-Tate group should be USP2G. One can also consider, one can consider both horizontal and vertical aspects of this Sato-Tate distribution. Instead of fixing a curve or an abelian variety and varying P, you could fix P or your favorite prime power Q and then vary over abelian varieties over that finite field, and you would expect to see the exact same distribution. Okay. So roughly speaking, in the large, we know exactly how Frobenius traces should be distributed, provided we can identify the Sato-Tate group, and that's sort of an interesting problem. And for dimensions up to 3, the Sato-Tate groups that can occur are now completely classified. There are 3 in dimension 1, 52 in dimension 2, and 410 in dimension 3. And each of them is a compactly group that has an associated Haar measure, which will tell you what the trace distribution should be for an abelian variety with that Sato-Tate group. And so here's just an example of what things look like in dimension 2. This is the exact same animation as we saw in the elliptic curve case, except now it's a genus 2 curve with the equation written up there. We're counting points mod p for lots and lots of primes, taking AP divided by square root of p, and then plotting real numbers that are now ranging from -4 to 4. And you see a nice smooth curve that reflects the trace distribution you would get if you sampled random matrices using USP4. And amazingly, even though we know exactly what this distribution should be, we can't prove this. In fact, we can't even, as Katz famously pointed out, we can't even prove that there's anything, I think, to the left or right of 1. Yeah, or I guess of 2. Yeah, we can't. So one way you could prove, if somebody secretly handled you an abelian surface, but you didn't tell you an equation, didn't tell you it was an abelian surface, and you wanted to prove that it had a dimension greater than 1, one thing you could do is you could count points mod p and at least find a prime where the point count is too large to be achieved or too small to be possible for an elliptic curve. Unfortunately, we don't know how to prove that. Not for even a single prime, never mind a positive density. Okay. Oops, sorry, I didn't mean to restart that. Let me go to the next slide. And there are a whole zoo of, instead of 3, there are, as I said, there are 52 Sato-Tate groups. There are 36 trace distributions that occur for genus 2 for abelian surfaces over number fields. Of those, 26 occur over Q. I'm showing some of them here. The only 2 that are relevant for this talk are this one here and this one here. This distribution is what you get if you had a product of elliptic curves or an abelian surface with real multiplication. So its Sato-Tate group looks like SU2 cross SU2 sitting inside USP4. And this one is very similar, but this group is the normalizer of SU2 cross SU2 inside USP4, which contains SU2 cross SU2 with index 2. And these are relevant to our discussion today because in this situation, while there are a couple of different ways it can happen, they all correspond to having a product of imprimitive degree 2L functions that are giving you your degree 4L function. Whereas if you're in this scenario, you're always going to have a primitive L function, degree 4L function. Okay. And I guess it's maybe worth noting in general, these compactly groups I'm talking about aren't connected. And here it's exactly it's not the identity component, but it's the component group that's making the difference.
So I can ask you a question?
Yeah, sure.
So these pictures, there are some sort of projection. I'm trying to sort of think like the space of conjugacy classes in USP4. It's like bigger than 1-dimensional. So you're
so one can draw beautiful pictures in 2 or even 3 dimensions. Peter has seen some of these. I'm just for this talk, we're just going to focus on trace distribution. So these are just histograms, but you're absolutely right. And there's a beautiful image, I think, that is maybe first suggested by Sayre. He had this vision of an island out in an idyllic ocean with a very particular shape that's given by, if you plot A1 and A2, and then you plot the density, that's the height of the island, and it has a very nice, gentle rise on one side, and then a very sharp slope down to the beach on the other side. Yeah, and of course, in dimension 3, it gets even more interesting. So but the one sort of very coarse picture of the abelian surface case is, so how do you go about classifying these Sato-Tate groups? This comes down to classifying real Galois modules, where your Galois module is a real endomorphism algebra equipped with an action of Galois. You classify those. It turns out there's exactly 52 possibilities. They all correspond to Sato-Tate groups. And there are exactly 6 possibilities for the identity component. And they're listed over here on the right. This is the generic case. This is the most special case. This would be something that's isogenous to the square of a CM elliptic curve. And I'm showing you the corresponding endomorphism algebra, and then the different ways you could realize this as an abelian surface. I mean, this is sort of coming from Albert's classification, but each of these different options is going to give you sort of maybe different ways of realizing these Sato-Tate groups for different types of L functions. Now, this is a very coarse picture here. One can say a lot more, and there is still work underway on nailing down exactly what are the details of all the different L functions and the automorphic connections that apply in each case. So I'm only going to sort of scratch the surface of this in this talk. But the main point to take away from this is we saw that in the large, the Sato-Tate group already has a significant impact on the Sato-Tate distribution. And when we're looking at sort of the fine detail coming from this murmurations phenomenon, you might ask, does the Sato-Tate group play a role? All right, there's another maybe more famous or equally famous source of influence on traces, distribution of Frobenius traces, and this is coming from the Birch and Swinnerton-Dyer conjecture at roughly the same time that Sato was running computer experiments and Tate was thinking about this problem. Birch and Swinnerton-Dyer were running computer experiments where they were.
Let me correct that. Sato was not running experiments, and we'll discuss this.
Okay,
He had somebody else calculating. He understood materials.
Yeah. We can talk about this later. Yeah, I have a nice letter from Sato about this. Okay, so, but of course, we know that certainly Birch and Swinnerton-Dyer did run computer experiments.
That's true.
In order to conformate their conjecture, they needed lots of point counts. And that's very relevant to this talk, because in order to produce some of the pictures I want to share with you today, one needs to count lots and lots of points. But what they noticed is, as you might expect that if you have an elliptic curve over Q with large rank, that you should observe an excess of points modulo small primes. Now, we already saw that from the Sato-Tate conjecture that sort of globally speaking, in limits, you don't see an excess. I mean, you get the nice smooth distribution. But in the error term, there is still an influence coming from the rank, and one can make this precise by conjecturing that this sum, so the x is going to infinity here, that this sum should converge to minus the rank plus a half. And I'm being intentionally vague about the rank here. I mean, of course, if BSD is true, there's only one rank. It's it's both the analytic and the algebraic rank. But this sums of this form are known as Mestrin-DeGrasse sums, and they're a standard tool that's used for finding elliptic curves of large rank. And in fact, one of the reasons Elke's curve is so skewed is not just because it was a rank 28 curve found in the wild. It's because he was sitting through families of L functions, specifically looking for curves that where this sum was very large early on, which would tend to mean it has very negative Frobenius traces at all the small primes. So in some sense, the method used to find elliptic curves of large rank tends to manufacture this bias, but we have theoretical reasons for believing that this should exist. And I should note the 1/2 here is quite important. And Mazur wrote a very nice article about sums of this form and various refinements of them entitled Finding Meaning in Error Terms. And Peter wrote McBarry a very nice letter refining making some comments on that article, and noting in particular, one thing that I thought was striking in the letter was noting in particular the relationship to the conductor and the fact, I mean, this is not hard to show. If you're going to have large rank, you have to have large conductor. And that's very relevant to, well, it indicates that the conductor plays a role here, but it's also relevant to the search for elliptic curves of large rank, especially if you're taking sort of a machine learning or a data science approach to it. If you might imagine that, well, what if we analyzed lots of elliptic curves with large rank and gave maybe the first million or first billion APs to our machine learning system and asked it to develop a means for predicting rank based on those APs. And what the role the conductor plays is that will work, tells you is that will work extremely well when conductors are small. And so one standard place you might go get elliptic curves would be in a database like the L functions and modular forms database, which has lots of elliptic curves, some 3 million of them. And in fact, they're the 3 million or so elliptic curves with the smallest possible conductors. And so that in particular, you'll have great success predicting ranks on elliptic curves in the LMFDB, but you'll find it much more difficult if you were to just write down a random elliptic curve, which may have a much larger conductor. And so there's a challenge there. At a minimum, you should have in mind that you should really expect to get no information from the first 8 APs for P up to something logarithmic in the conductor, because just by the Chinese remainder theorem, I mean, I can concoct an elliptic curve with exactly the traces I want in any finite set of primes by just applying CRT. That'll make the conductor huge, of course, but I can arrange an elliptic curve to have APs I choose at small primes. On the flip side, there's another tension coming in the other direction, which tells strong multiplicity 1, which can be made effective, tells us that if we know the APs up to roughly the square root of the conductor, we've completely determined the L function, including knowing what its analytic rank is. And I just mentioned this sum. I wanted to maybe advertise this theorem, which in some sense tells you this is going to be a very hard thing to prove, because what this theorem tells you is that, well, it tells you a comforting thing, which is that if the limit on the left-hand side exists, it is equal to the value on the right. On the other hand, it also tells you that if you can prove this, you can also prove that the L function of E satisfies the Riemann hypothesis, which is not something you're likely to do anytime soon.
Don't underestimate people.
Yes, I shouldn't. I don't want to discourage anyone in the argument that please prove the Riemann hypothesis for all functions of elliptic curves. And I wanted to give you some sense of how good these Mester-Nagel sums are at predicting ranks. So these are, I picked the 28 elliptic curves of ranks going, or 29 rather, going from rank 0 to 28, and found the ones with the smallest conductor I could find, and then computed these Mester-Nagel sums out to with P going up to 10 to the 12. And so each of these lines should be converging, should be heading towards R minus a half. And you can see it hits it almost on the nose when the rank is small, which means the conductor is small because I'm taking small conductors. But as you get bigger, like for Elke's, rank 28 curve, it's nowhere near 27 and a half, minus 27 and a half. It's 10 to the 12th is just way too small. And here's a similar chart for CM elliptic curves. I think these are all twists of the Mordell curve. All right, so now that brings me to the main topic for today, which is the topic of murmurations. As Nina mentioned yesterday, in a rather startling, or at least startling to me, preprint in 2022, he, Lee, Oliver, and Pozdnyakov observed a rather curious phenomenon in experiments they were conducting where they were doing exactly what I said. They were taking elliptic curves from sources like the LMFDB and trying to train a machine learning model, a neural network, to recognize various, not just the rank, but various arithmetic invariants one might associate to an elliptic curve. You would first train it on giving it the invariant you're interested in, plus maybe a bunch of APs or other invariants, and then asking it to try and do sort of dimension reduction analysis that will allow it to come up with a good source of input to your machine learning model. This is really like the first step in a machine learning exercise. And one thing that was observed, and I think it was actually Alexei who observed this, you may have heard in the literature, or in the news, people talk about machine learning and large language models and AI, and how there's these inscrutable matrices that you can't really understand what they're doing. But in a scenario as structured as this, where we actually know what every variable is, and in this case, the matrix is the column, each row is a sample, say an elliptic curve, the columns are the rank and then a bunch of APs. The first step is to form a covariance matrix and compute its eigenvalues and its eigenvectors. This is principal component analysis. And then you're going to feed the weights coming from that principal component analysis into your machine learning model. And one thing that I believe Alexei noticed when he looked at the weights was a fluctuation in the sign in the weights. And that's what led them to conduct additional experiments and observe this remarkable phenomenon, which they termed murmurations. So what you're seeing in this picture here is we're taking a family of elliptic curves with conductor ranging from 7,500 up to 10,000. There's rough, and then dividing them by rank. There's about 4,000 of rank 0 and about 5,000 of rank 1. And then for each of the rank 0 curves, we're taking for each prime, p going from 0 up to 1,000 in this picture, we're going to add up, we're going to compute the average value of the traces of all the rank 0 curves and of AP, and the average value of AP for all the rank 1 curves. And we'll put a blue dot at p, or I think this is actually the index of p, and the average value if it's a rank from the rank 0 set, and a red dot for the rank 1 set. And if you think about what we know about BSD, what should surprise you, the first part of this picture shouldn't surprise you. You should expect the blue dots to have positive trace, because that means they have fewer points mod p, and you should expect the red dots to have negative trace, meaning they have more. But what's surprising is that they cross over. So this suggests a bar game you could play. If you walked into the right bar, you could let someone pick an elliptic curve, and they would tell you they'd be required to tell you the rank and the conductor. And then you get to choose a prime, and then you place bets on where their AP is positive or negative. And if you know this picture, or even if you just know where these crossover points are, you're in a good position to make money off of those bets. You might have to bet a lot to make money off it, but eventually you do quite well. Yeah, so I found this quite striking. They sent me an early preprint of this paper. I got very interested in trying to understand this phenomenon. And especially because I do a lot of work with the L functions and modular forms database, and I'm often thinking about sort of L functions and higher dimensional analogs of elliptic curves. I wanted to know, is this something specific to elliptic curves, or does it generalize to other types of L functions? And so what I'd like to share with you today is some of the results we found. This is very much in progress. And I should mention that Hua Huan Li is in the audience with us today, one of the authors of the Murmurations paper, and I'm working with him, and Yang and Tom and Alexei were working together and trying to catalog some of the results that we found to give you more fodder for proving wonderful theorems like the theorem that Nina proved yesterday. I should say that in the rest of this talk, there will be no theorems, no proofs, maybe a few very weak conjectures, but my hope is to give you something to think about and perhaps prove and present in a later talk. Question? Yeah.
How does the picture change if you look at, instead of the average of AP, you look at higher moments like the average of the squares or the cubes?
Yeah, great question. And that's not, so I have anticipated several questions. Unfortunately, that's not one I have anticipated. I do not have a slide for that question, but that's another reason to give this talk. I mean, in some sense, this is a little premature. Usually you give a talk after you've proved the theorem and the preprint is up and everything is polished and perfect. But I felt like it would be good to share these results precisely so we would get questions like, did you try this or that or the other thing? So yeah, that's an interesting question.
But there are histograms in the picture. You can see, we didn't calculate higher moments, but you can see the histograms.
Yeah, so there is, I'm going to be focusing on one very specific aspect of the phenomenon, but yeah, I would encourage you to check out their Murmurations paper. There's also detail on the PCA, on the principal component analysis, that will also shed some light on sort of other aspects of the distribution beyond the averages. Okay, so the first thing I wanted to do when I saw this was to try it on a lot more elliptic curves and throw a lot more computational power at it. So I ran a similar experiment on all the curves in the LMFTB, about 3 million of them, because I suspected that this was really, I mean, the sequence of traces is really just a property of the L function, not the elliptic curve per se. And since I'm an L function, I think about L functions a lot. I wanted to really focus on L functions. So I'm always taking, throughout the rest of this talk, I'm always thinking about isogeny classes of abelian varieties. If I'm mentioning an abelian variety or an isogeny class of a Jacobian, if I'm taking a curve. So I'm only counting each isogeny class once. For elliptic curves, that doesn't really matter. The typical elliptic curve isogeny class has cardinality 1, but just to be clear, when the numbers are small, the isogeny classes can get bigger, and I didn't want to have that skewing the numbers. So I'm taking each isogeny class once, and I'm taking a dyadic interval of conductors from M to 2M, and then I'm taking all the elliptic curves, and in this case, I'm restricting to non-CM because I want to have Sato-Tate group SU2, just not to throw in, the CM curves are 0% of them, so it's not really going to make a difference, but just to keep things clean, let's just focus on the L functions with Sato-Tate group SU2. And then I'm going to compute this murmuration diagram with blue dots and red dots, just as we saw in the murmurations paper, and making M as big as I can. Okay, so let's go ahead and play this. So in each interval, M is doubling, and so we're getting our, our flock of elliptic curves are growing, but they stay very much in formation. I mean, if anything, as things get better, the bigger the number of points gets bigger, the pattern becomes even clearer.
Sorry, I want to clarify that point. So when you went to very large n, what would you expect to see here?
So as long as I'm keeping, so I should mention P is running from
P
0 up
scale.
to n. If
That's
P
right.
goes to infinity, it's going to get noisy.
Same scale.
But I would expect, this blue and this red line to get even more darker and darker and darker. There's still going to be cruft floating down.
So you would expect it to somehow the variance to reduce.
Yeah, I would say, if we're measuring, yes, I would expect the variance to reduce. And I'll notice that the crossover points and the amplitudes are not changing as we're increasing the conductor.
And okay, I think like then Nina's talk does not fully explain that phenomenon. I think if you expect the variance.
I agree with that. I'm going to also talk, just to give a foreshadowing, I'm going to talk about a slightly different average one can compute that will make these curves a lot sharper than they appear in this picture. But I want you to appreciate that even with this very sort of basic experiment, the data is pretty compelling. And I'll also mention that it's shocking to me that this wasn't observed before, because you don't actually need a lot of data. I mean, this was a lot of computation, the last frame in this animation, but the first frame wasn't a lot. Anybody could do this. Yeah. In fact, you could probably write, a Magma script that you could run in less than 2 minutes in the Magma calculator that would already convince you of this pattern.
Probably not, but you might be.
But I will say that for me, I think what excites me about this project and got me interested in it is not the machine learning or the artificial intelligence spin on it. It's more the notion of taking an observational approach to mathematics. This is really just a data science. People were looking at the data. They found something interesting that demands explanation. I ran to everybody. I knew every number theorist I could think of who I thought might know the answer off the top of my head. And to date, no one has reeled off an answer, although we have at least Nina has shed some light on the question, but there's still many questions to be answered.
Is there any reason that the noise sort of goes downwards from the actual curves? Like, is there like an error term somewhere to explain this?
Yeah, good question. Let me hold that one and come back after I show you the different averaging I want to do, where this fuzz will disappear. But I will say there's one obvious source. Maybe I shouldn't be too cagey about it. There's one obvious source of noise here, which is if I tell you the conductor is the key invariant here, well, I'm averaging over curves in a pretty big interval from M to 2M. The curves at the left-hand side of the interval have very different conductors than the curves on the right. So we shouldn't expect things to line up perfectly when we're making our interval that big. On the other hand, if we made the interval too narrow, then we don't have enough data points, and we should expect noise just coming from just not a large enough sample. So there's a tension there. Yeah.
By going downwards, I mean like literally below the actual.
Why are they always dropping? Yeah, that's a good question. I don't know the answer to that.
Okay.
Yeah, we'll see some fuzz in other directions in some of the other slides. Any other questions? All right. So the first suggestion I had, and I think this is a very standard suggestion, if you talk to anyone in arithmetic statistics, I mean, in some sense, this is a question about arithmetic statistics. The first thing they're going to want to do is, well, a conductor, is say, why are we ordering by conductor? That's ordering by conductor makes it hard to analyze things using standard techniques. We'd rather order by height, by naive height. Most of the major theorems we know about averages for elliptic curves, for example, average ranks, the work of Bhargava and Shankar and others, all amount to averaging by height. And the standard motivation for doing so is, well, there's two motivations. One, it's easier, but the other is it shouldn't really matter asymptotically. I mean, as the height grows, the discriminant grows, the conductor is bounded by the discriminant. These really ought to all be the same thing and should always, we should get the same answer no matter how we order, as long as our ordering is reasonable. Don't order by rank or something silly, but if you order by, whether you order by naive height or conductor or discriminant isn't supposed to make a difference. So that was the next experiment I tried, was to try ordering by other things. So in this, I have three charts here. The top one, this is ordering by naive height. So the absolute value of a cubed, maximum of the absolute value of a cubed, b squared, where our elliptic curve is y squared equals x cubed plus ax plus b. Ordering by the absolute value of the discriminant, minimal discriminant, or ordering by the height of the J invariant. We're talking about elliptic curves over Q, so this is a rational number. Just take the max of the absolute value of the numerator and the denominator. So three different ways you might naively order your elliptic curves over Q. And in the first frame here, maybe I'm looking at only maybe 1,000 sample points for each of these orderings. The pictures look pretty fuzzy, but maybe there's a murmuration pattern in there. Maybe we just need to go further and the murmurations will appear. Right, I mean, asymptotically, the motivation says that if you order, whether you order by height or by conductor, maybe it'll make a difference when things are small, but in the limit, they should give you the same answer. So let's hoop.
Sorry, Drew, how many elliptic curves are in that set at the upper edge, 250,000?
On the previous slide, at the top, there were about 2 million isogeny classes, so about 1 million were contributing to blue dots and about 1 million contributing to red dots. And in this picture, the numbers are comparable at the limit, not in this first frame. Let's go look at ordering by naive height. Okay, so we're waiting for the murmurations to appear. And they don't seem to be there. Don't be confused by the red here. I'm plotting the blue dots first and the red dots second. So that just means the red wins when they're on the same pixel. Okay, it doesn't mean there's more red. Okay. Yeah. All right, let's try by discriminant, which is very close to naive height, but there could be cancellation, and the discriminant is closer to the conductor, so this is a reasonable thing to try. Again, just a lot of white noise, maybe not slightly different. You can see it's not the same as ordering by height, but no murmurations in sight. All right, let's try by J invariant. Interesting. It doesn't. It stays a little closer to the origin, but there's definitely no separation between rank 0 and rank 1. Again, the red is here just because there's red dots on top of blue dots. If I plotted the blue dots first or the second, it would be all blue. Okay. You could also ask about Falting's height. I don't actually know how to order elliptic curves by Falting's height. If somebody does know how to do that, I'd love to know. Like, can you give me an effective algorithm for enumerating the elliptic curves of, say, Falting's height up to 2? I don't know of anyone who has an algorithm to do that, even though we had to have theorems that tell us, well, it's basically just the naive height is bounded by the naive height, but that doesn't give you a very good algorithm unless your bounds are really, really tight, and they're not. They're way too big to make that a practical algorithm. Okay, but I would expect it to be similar to this picture. Okay. I did try using the Falting's heights that we know in the LMF DVD, but those aren't sufficient. Okay, so now I want to generalize this, consider other L functions. I want to at least just say a few words about the class of L functions I want to talk about, because I know we have people in this audience who think about much broader classes of L functions than I tend to. I'm going to focus on arithmetic L functions, so there will be no Moss form L functions in this talk, although that I'd welcome suggestions for how one might think about this phenomenon in that setting. So I'm going to focus on sort of a subclass of L functions, which are sometimes called analytic L functions, which are L functions in the Selberg class with some additional constraints. They satisfy all the things a good L function should: analytic continuation, functional equation. I want an Euler product because I want to be able to compute Euler factors. There should be growth conditions on the APs, should satisfy the Ramanujan bound and the Selberg bound, and there should be a central character. I'll refer you to the paper for details. Among all analytic L functions, I'm going to be even more picky and distinguish those that are arithmetic, meaning that I can get algebraic integers. I can make the coefficients algebraic integers. I'm assuming this is in the analytic normalization, but I can effectively undo that effect by multiplying by an appropriate power of the integer, which is going to be w over 2 for some integer w. The least such integer w is called the motivic weight. There's an unfortunate collision of terminology here. The motivic weight is not the same weight as the weight of a modular form. It's off by 1. So a modular form of weight 2 has motivic weight 1. Abelian varieties have motivic weight 1. All the L functions, most of the L functions we're going to see in this talk are motivic weight 1, but we'll see a few of weights 3 and 5. I'm also going to assume that all the families of L functions, arithmetic L functions we're considering, I want them to be algebraic integers so I can construct Galois orbits, and I want all the families to be Galois closed. Meaning, if you give me an L function that doesn't have rational coefficients, I can multiply by all of its conjugates and get a higher degree L, imprimitive higher degree L function with rational coefficients. And so that means when we average APs over any such set, we're always going to get integers, right? Or when we add up, when we sum the APs, when we take the average, we're going to get real numbers. But the one reason the motivic weight is relevant is that it tells you what you should normalize by. And this normalization is important when you want to look at modular forms that aren't weight 2. The normalization is you should divide by p to the w minus 1 over 2, where w is the motivic weight. And for modular forms of weight 2 and abelian varieties, w is 1, and so you're not doing anything. That's p to the 0. But in general, you need to include that factor, or you're not going to see the murmurations. So here, I'm just going to click through these quickly because we saw these in Nina's talk yesterday. So these are L functions of weight 2 cusp forms. In the first picture, I'm just considering cases where their Galois orbits have size 1, so these are rational coefficients. The second one, these are Galois orbits of size 2, so their coefficients are in a quadratic field. These correspond to modular abelian surfaces, if I were to apply Eichler-Schmor to construct that. And then in the last frame, I'm considering all modular forms with trivial character at that level. This is exactly the function that Nina was studying, and in a few slides, we'll see when we change the normalization to do local averaging, we'll see the Zuppelina function, but you can already see this curve that she explained. So this is the one part of this talk where we actually have a theorem. This is what you will get if you go to infinity. Let's try weight 4. So here I'm dividing AP by P in each case, because that's W, the motivic weight is 3, 3 minus 1 over 2 is 1. So I'm dividing by P to 1. And you can see, again, you can see murmurations. It's hard to get data here because as the weight goes up, the complexity of getting the data is growing to the square of the weight and also with the level. It's really more natural to think of the analytic conductor, which is proportional to k squared times n. So when k gets big, it gets harder. But you'll notice when we take all modular forms, we get a very sharp, distinctive curve. I'm sure there's an explanation that can be applied here using the same similar techniques, but notice this is different. This is not the same curve we saw in weight 2. And now we can go to weight 6. Same thing again. And again, the murmurations get fuzzier, the crossover points are changing, but I think hopefully you can still convince that there are murmurations to be seen, and certainly this frame makes it clear. So as I think Nina mentioned yesterday, the rate of convergence is very fast when you're doing these computations for all new forms for gamma naught. All right, and here I've just sort of captured the 3 weights that I computed when I'm averaging over all new forms. This is weight 2, weight 4, weight 6. Okay, so it'd be nice to have a theorem, a generalization of Nina's theorem that covers these cases and even k going to infinity. One could also ask about odd weight. There, of course, we're going to need to introduce a character, and then one could ask, should you fix the character, or maybe we should just apply the trace formula over all of gamma 1. Yeah, I'm sure there are techniques that can be applied. Okay, and now now I'm including the sign in the averaging. So if the root number is I'm multiplying by the root number. So now instead of getting 2 curves, I just get a single curve. And so you can see they line up very nicely. And again, the curves are slightly different depending on which weight you're in. Okay, so that's it for modular forms. Well, I will come back to them at the end. Any questions? Okay. All right. So one natural way to generalize from elliptic curves was to look at modular forms and change the weight. Now I want to generalize in a different way and increase the dimension of our abelian varieties. So elliptic curves are abelian varieties at dimension 1. Let's think about abelian varieties dimension 2. And conveniently, if you go to the LMFDB, you'll find there's not that many genus 2 curves in the LMFDB. I mean, it might seem like a lot. 66,000 or so, that might seem like a lot, but in scopes of experiments like this, that's nothing. You need a lot more data than that. But we have a new data set of about 5 million genus 2 curves of small conductor. And by small here, I mean conductor at most 2 to the 20. And so I used that data set in all of these experiments. In that data set, there are about 1.4 million isogeny classes of genus 2 curves that have generic Sato-Tate groups, so USP4. Okay. So this is the analog.
I'm looking at them, all of them ordered by conductor.
I'm looking at all of them isogeny classes. So I'm only taking one L function per isogeny class, and I'm ordering them by conductor. And so here I'm running exactly the experiment I ran for elliptic curves. With one caveat, I can't prove completeness here. In fact, I can tell you it's not complete. There are definitely abelian surfaces we're missing, but we've put a lot of effort into finding these, so I'm fairly confident we have most of them. So I wouldn't expect the pictures to change. And we certainly have enough to make the murmurations very clear, although the pattern is quite different than what you see in for elliptic curves. We also see the same sort of snow drifting down that we saw in the elliptic curve case. And this new data set will be getting added to the LMFDB later this year. So now I want to consider genus 2 curves with a different Sato-Tate group. So rather than taking USP4, I mean, this isn't such an interesting thing to do in the elliptic curve case because there's only 13 elliptic curves over Q, in fact, up to twist with that have complex multiplication. But over in dimension 2, you have infinite families and even 2-dimensional families. The generic family has dimension, module space has dimension 3. So this is maybe an interesting case to look at. So I'm going to look at abelian surfaces with Sato-Tate group SU2 cross SU2. There's actually 2 ways these can arise. These correspond to either a product of elliptic curves, or they correspond to an abelian surface coming from a weight 2 new form with quadratic coefficient fields. So these are going to have real multiplication. But in this data set, the products of elliptic curves completely dominate. So that's what most of these are. But in either case, the L functions are imprimitive. So we're really taking the product of 2 L functions when we do this. And you'll see that maybe at the very beginning, there's a little bit of separation, but in general, there's not much of a murmuration pattern to be seen here. But we'll come back, hold this one in your head because we're going to come back to it. Here's a slightly different Sato-Tate group. I mentioned earlier, the normalizer of SU2 cross SU2. These arise for elliptic curves whose Jacobians correspond to or they have L functions that correspond coming from a Hilbert or Bianchi modular form. Okay. Hilbert modular forms, or at least one subset of Hilbert modular forms, correspond to elliptic curves over quadratic fields. Bianchi modular forms correspond to elliptic curves over real quadratic fields for Hilbert, imaginary quadratic for Bianchi. And we have databases of Hilbert modular forms and Bianchi modular forms and corresponding elliptic curves in the LMFDB. It's not quite a one-to-one correspondence. There are, for example, Bianchi modular forms for which there is no corresponding elliptic curve, but there almost always is. So let's go ahead and run this case here. And yeah, again, a lot of noise, but maybe I'm seeing what I want to see here, but I'll suggest that there's a little bit of a pattern, more than there was in the other case. But it'd be nice if we had a way of picking that out.
But I assume the size of this set is much smaller than.
Well,
Like
yeah, it is.
17.
Yeah, you're right. Like about a 10th. Yeah, it is much smaller. That's a fair comment. Yeah, it's as big as I could get it, but I can't. I just can't make it as big as I would like to. All right. So now in the last 15 minutes, I want to discuss some very recent work, or recent for me, but I should give credit where credit is due. This is an idea that was suggested to me by Jonathan Bober, who I hope is on Zoom, or at least I see Andy, but yeah, John is here. And which is sort of a natural idea. We're rather than thinking about elliptic curves, we know the conductor plays a role. Rather than averaging APs over elliptic curves with bounded conductor. If you think about it, and we were always taking P up to maybe the bottom of the interval. If you think about it, what really matters, like where those crossover points are in the curves, is the ratio of P to the conductor. And so maybe what we should really be doing is, what we'd really like is to change the x-axis. Rather than having the x-axis be P, we'd like the x-axis to be P over the conductor. And this would allow us to consider not constrain our family so much. We wouldn't have to constrain the interval in which the family lies. We could consider, and it might also impact how we have to order things if we sort of bake the role of the conductor into our sampling. And so in order to do that, we were going to, some of the elliptic curves in our family might have huge conductors relative to someone who's right next to them. So in order to handle that situation, what we're going to do is we're going to compute local averages, where for each L function in our collection, we're going to divide the range from 0 up to, say, 1 or 2, where 1 or 2 is representing the maximum ratio of N over, of P over the conductor. You can go, as Nina did in her talk, you could take that ratio up into the tens or hundreds, but I'm going to focus on the computationally accessible region where that bound is going to be like 1 or 2. For the sake of arguments, let's just stick to what we were doing in all of our dyadic interval experiments, where we were taking the ratio up to the p over n was going up to 1. And so I'm going to divide that interval for, depending on n, that's going to be a different range of p. So for each L function, I'm going to have to compute all the APs up to the conductor, whatever the conductor is. And then I'm going to divide them up into 1,000, partition them into 1,000 sets. And then within each of those thousands, based on those subintervals, I'm going to compute an average AP. And now I'm going to imagine that my L function, instead of having all these APs, just had 1,000 of them. These, averages, real numbers. And so I get a vector of real numbers, 1,000 real numbers for each of L function. And then I average those vectors. This is not exactly what Bober originally suggested, but I'm not going to go into the details now. I like this approach better because it doesn't unfairly bias elliptic curves with very large conductors who, if you were to just compute all, rather than doing this local averaging first, if you just averaged everything, the elliptic curves with very large conductors would, in my view, have undue influence. Maybe it doesn't make a difference in the asymptotic, but I want to keep things fair, especially because in the families that I'm working with, where it's feasible to do these computations, the conductors can't get too large. Now, in this setup, as I alluded to, the ordering doesn't necessarily matter. We don't have to order by conductor because the influence of the conductor is already baked into the problem. It's sitting there in this denominator. But interestingly, the order still matters. So I'm going to show you some plots. So here are 2 plots. The first is one we've seen before, ordering by conductor, but we're now doing our local averaging. And you'll notice the amplitude is growing initially, but then it stabilizes. So that's not a theorem, but I will predict that I think that's stabilizing to a fixed curve. And notice there's no snow, there's no red and blue dots drifting down anymore. That's disappeared from this picture, except for occasional weird outliers, like what the heck is that blue dot doing there? I have no idea. Sometimes birds stray from the flock, it happens. All right, now let's see what happens when we order by height instead. Actually, before I click this button, are there any predictions? Let's wager bets. Who thinks this picture is going to wind up looking like this? Any hands?
I'd like to say yes with the way you're talking.
Yeah, exactly. I'm giving away the game. Yeah. Let's click and see. Yeah, so crossover points are definitely sort of there, but there's like a double, sort of a fractally thing going on. Notice these peaks are repeated. I realize I'm getting tight on time, so rather than, I have various speculations, but there's lots more I want to show you, and I would make sure I get to that. So I'll leave you just with the statement that they're different. I think there's some ways you could explain part of this difference.
You said there is no snow, but it still looks like they're kind of a little below average. So
yeah, good point. Yeah, let's the crossover is slightly below. Why is that? Yeah, I think
overall.
Yeah, overall they're shifted. Yeah, that's a good observation, and we'll see it'll be relevant in a few slides. Yeah. Yep.
So in your previous experiments, did you show the averaging with respect to height? It was white noise.
It was white noise, yeah.
What was the?
What's different here is I'm now computing local averages. I'm looking at P over N, the ratio. I'm putting the conductor in the denominator. So in some sense, you should think of it as that noise was there because the x-axis was not organized correctly. The P's were just going wherever they wanted, but I'm shifting them around. I'm collecting all the P's so that they're lining up in the right place relative to the conductor. What matters is how big is P relative to the conductor? And that's one of the reasons I mentioned earlier when I was talking about Birch, Swinnerton-Dyer and strong multiplicity 1, that how big P is, what matters is what is the conductor. And if you don't know the conductor, it's not really, you can't really say much.
Thanks.
Right. And here's another plot. I'm not going to show you the animation because the animation is basically the same. But so far, all the plots I've been showing you, I'm just looking at root number, +1, -1, odd rank, or even rank, odd rank.
I think that outlier you had before was actually a speck of dirt on the projector.
Yes, this reminds me of a debate, I think it was Newton and Leibniz, between notations for the derivative, that you shouldn't use dot for the derivative because you didn't want a fly to be able to differentiate the function. Yeah, but there are outliers. Okay, this one is definitely not a spec. All right, so here, blue is rank 0, red is rank 1, green is rank 2, and these brownish things are rank 3. Now, there are a lot fewer rank 2 and rank 3. There's quite a few rank 2, though, at small, even though you know 100% of them are blue and red. When you're looking at bounded conductor or bounded height, there's actually quite a few rank 2s, tens of thousands. There's a lot fewer, maybe only a few thousand rank 3. So this is not a huge sample size. But I think you can already see that there's some distinctive sort of sub fluctuations in the rank 3 case that you don't see, especially even, yeah, so I shouldn't point at this picture. I should point at this one. The red and the blue are much smoother than the green and the brown. Yeah. And you'll notice that they're all shifted. The other thing I should point out is green is shifted. You should expect the green curve and the blue curve to be correlated because they have the same root number, but you should expect the green curve to be slightly below because it has higher rank. It should have more negative APs. Yeah, question.
I'm not sure if it is a question, but I noticed maybe it's just what you said right now, but the blue and the green seem to have like opposite small fluctuations all over the place. Is it meaningful or expected?
I think it's too early to say what is and is not meaningful. I spent a lot of time staring at these pictures. I only made this plot within the last few days. And yeah, basically my initial reaction is jaw drop and stare and think. And I think we're still at that stage. I don't know what it means yet.
Sorry, okay, these, you're going to explain the relation of those to the next one. Right? The next curve that you
yeah, so
that's Nina's curve.
Yeah, so I now want to return to the modular form setting, but instead of doing dyadic intervals, I'm going to apply our local averaging, which also showed up in Nina's talk. Although the local averaging I'm doing is slightly different, but you'll see that you get almost exactly the same curve. But these are for weight 2, 4, and 6. I think a word of caution is in order for the rank. I'm not confident that I have enough weights in weight 6 to be sure that this has stabilized as possible.
This local averaging and what Nina was calling local averaging is your interpretation of Boba local averaging, Nina's local averaging are the same thing. Is that correct or not?
They're not mathematically the same thing. They do similar pictures.
So the picture, like the top one there is Nina's, right? You can prove that, I think.
Yeah. Let's go to this slide. It's even clearer here. I think you saw this in Nina's talk.
That's slightly different average, right?
Yeah, but the average is different, but the curve, I think, is the same curve. Yeah, this would be my guess. I mean, Nina asked me to run this experiment, and she sent me her curve, and realized it was going to take me time to implement the experiment that Nina was asking for, and it's harder to compute, but I already had something that looked very similar, so I sent her mine, and the pictures line up very, very well. This is weight 4, this is weight 6. All right, now I want to look at what happens when we look at USP4 functions. These are both plots for USP4. This is by root number. Here I'm multiplying by sign to get a single curve. But you'll see again that it's even more noticeable in the genus 2 case how much it cleans up the shape of the curves when you do the local averaging. In this plot, I'm doing SU2 cross SU2 versus the normal divisor of SU2 cross SU2L functions. And here you'll see that with the local averaging, we definitely can pick up oscillations where I claimed I could see them.
Yeah.
But here, not so clear what's happening there.
So the dyadic averaging was smearing it out.
Yeah, the dyadic averaging was smearing it out. That's my takeaway from these experiments. And here I wanted to address, I'm not sure this is exactly the question that Akshay asked, but I wanted to address it because I realized I had a data set that could answer this question. So I said when you have the normalizer of SU2 cross SU2, it could be coming from a Hilbert modular form or a Bianchi modular form corresponding to elliptic curves over real quadratic fields or imaginary quadratic fields. And you might ask, are they different? Is there a difference between the real and the imaginary case? I could imagine one of these being much easier to prove than the other. Generally, Hilbert modular forms are a lot easier to work with than Bianchi modular forms. But you'll see that the distributions it doesn't seem to matter. The distributions look the same. And then lastly, I wanted to show you a plot, a rank plots, where now I've separated out rank 0, 1, 2, 3, 4. This is for SU2 cross, this is the original elliptic curve, just SU2. And then this is USP4, genus 2 curves.
So getting back to this variance, the variance seems to have shrunk once you do this local average.
Yeah.
Wow.
Quite dramatically. Yeah, I'm excited about this. Yeah. I have a few more slides, but I think I'm getting tight on time, so maybe I'll stop there. And if someone asks a question that is answered by one of my later slides, I'll flip to it.
All right. Food for thought.
Can you show us your later slides?
Sam, if you left, could we continue with the slides a bit?
I mean,
Let's say maximum with slides, another 5 minutes.
Okay, all right, let's go through this.
and the call.
Yeah, so one.
Because I know that we can use the blackboard once you've left.
Yeah. So one example I wanted to show is if you could ask, does this murmuration pattern happen within a family of quadratic twists? Fix a single elliptic curve. Let's take 11A1 and consider all of its quadratic twists. Okay, I say it's a thin family because the conductor is growing quadratically in that family, and the IV height is like growing to the 6th power. So things get big really quickly. And if you do the dyadic, it's sort of hopeless to try and treat that using a dyadic interval approach. But with the local averaging, again, it's not as much data as I would like, but I think it's clear that the fluctuations, the oscillations are there. So this is in a very thin family. And the last, sorry.
Now I'm shocked.
Good. Mission accomplished. Mission accomplished.
No, it's just that if you do naive height, it's gone. But if you do, it's still conductor in this family. Of course, you can make one parameter families do anything you want with root numbers. You know, these examples of Rawley.
Yeah. So last slide I wanted to show, and this was something I've been thinking about, especially more after Nina's talk, and I made a few plots last night. I want to redo these. But one could ask that, one looks at these plots where the periods are growing, and you might think we have the wrong scale. And it's pretty clear from Nina's results that the right scales, we really like to basically replace x with the square root of x, at least in the interval from 0 to 1. And that's what I've done here in this plot. And it changes the shapes of the patterns. It's very thin here just because I don't have enough data here. I should rerun the local averaging using different binning where the sizes of the bins are growing quadratically. But it also makes it a lot easier to see what's going on in the genus 2 case as well. So that's, to sort of stay tuned for additional results. I think we should also be looking at how we're scaling this x-axis in these plots.
Actually, let me suggest that there may be people on the Zoom who want to ask questions, and since they're going to be cut off first, and then when you finish your talk, I will stay here for a while, and maybe many others. So unmute yourself and, as they say, ask a question. All right, well, I think then we can end the talk, and anybody who wants to continue discussing murmurations, you're here for the day, so we can continue. And let's thank both speakers for